ready ke tak ready. Contoh macam saya lah. Bangi ready. Kita nak tengok 46 peserta ni bersemangat ke tak pagi ni? Wow, ada yang daripada Sarawak, Nigeria, oh, international. Kuching Sarawak ready, Ipoh ready, UiTM Shah Alam ready, Bandar Baru Bangi siap sedia. Kuantan ready, Melaka ready, Shah Alam ready, Ceras ready, Sungai Buloh ready. Oh, Sungai Buloh, how is Sungai Buloh today? Banjir okay? Dah reda?
Dah okey dah, alhamdulillah.
Oh, okay, alhamdulillah. UKM Bangi ready, Shah Alam ready. Ramai daripada Bangi Kita ada 47 peserta. Chemical Engineering UMP ready. Okay. Good. Syazwan, peserta kita semua berapa orang?
Ikutkan lebih kurang 100 lebih.
Yang register?
Yes.
Okey, ramai lagi ni. Baru 1/3. So, kita tunggu sikit lagi. 9-5 minit lah kot kita start. UiTM Shah Alam dan Ceras. Okay. 50%, 50 participant. Okay, half to go. $54. Come on, guys. Still 54. Okay, while we are waiting for others, I would like to introduce myself first. My name is Azri, and I will be your moderator for today's webinar. Okay, before we start, I would like to go through some housekeeping rules and also a few announcements lah. Okay, first, please mute your microphone and video throughout the webinar. And then if you have a question, please use the chat box. And then your question will be entertained soon by either speakers or our staff members lah. And then 3, please fill up the feedback form in the chat box at the end of the webinar. Okay. link will be given at the end of the webinar, maybe around 11:30 or 11:45, 15 to 30 minutes before our webinar end. And then slide and webinar recording will be emailed upon the completion of the feedback form. So if you wish to get the slide and webinar recording, please complete the feedback form lah for us. Okay, your cooperation is highly appreciated. Sorry. Okay, next. Sharp with slide QR code. Sharp. Okay. This is what we are offering to our client. Okay. Basically, we are analytical service lab that provide instrumentation and capacity building service, which cover five what we call it segment: elemental analysis, microimaging, chemical structure, failure analysis, life science, and natural product. So if you have a question or you want to get more information, please scan those QR code. Okay, those QR code will bring you to 3 different source of our social media. First is website, which is www.ukm.my/i-CRIM. And then second, our Facebook page. Feel free to like our Facebook page. And then lastly is our Telegram channel. So this Telegram channel is our new channel for what we call it. If you have any question and then need urgent response, so you can use this channel Telegram. Okay. So please scan the QR code while we are waiting for other members. We are okay. Half to go. We are expecting 100 participants, but only half. Okay. Next, I would like to get everyone attention for our service promotion. Shark, promotion slide. No, Pukal. Nak start ni dulu. Okay, tak apalah. I will start with this first. Okay, for your information, i-CRIM Lab has a new instrument for WDXRF, which capable of micro mapping. Okay, and then we use a tube above X-ray, different from regular WDXRF lah. So this is a new technology from Rigaku. Okay. So if you can see the slide here. So this is the instrument Rigaku model Primus 4, and then sample requirement as stated in the poster, and then for service charge. Okay, we after 1 month, I think 1 or 2 months of installation and commissioning and testing, now we are ready to open for service. Okay, so basically there are two types of analysis that we can provide to you. First is elemental and oxide group analysis, and then second analysis is micro mapping, and the price is as stated for internal customer and external customer. There will be a difference in terms of the cost. So basically, if you want to know more, you can download the form at our website. Okay. And then lastly, for promotion, Syak poster. Okay. For poster, Syak, poster bukan? Tak ada eh?
Yang buka tu nanti kita masuk masa kat ujung.
Oh, okay. Okay lah. So, without further ado, I will turn my time to our speaker today. But first, let me introduce our speaker, our first speaker. Syak, can you share the biodata slide? Okay, this is our first speaker, Mr. Kelvin Koh Yen Bin. He is our SRD and SRS specialist from RGS Corporation Sdn Bhd. He started his career as a service engineer who specialized in servicing X-ray instrument. And then by 2006, he changed his job focus as an application specialist in X-ray diffraction. And then after that, he was promoted to product specialist for SRF and SRD with specialty in mineral, geological and building material. And then after that, in year 2017 until now, he moved to RGS Corporation as a product manager, where he was responsible for analytical equipment for various field and application. Okay, so now I will invite Mr. Kelvin to start our webinar. Thank you.
Okay. Thanks a lot, Mr. Azri, and then thanks UCAM for giving us this opportunity to present about our this product. And then we hope this actually could be beneficial for you guys. So just wondering, is that can you guys see my my screen, the screen which I share? So Azri, can you confirm that actually can you see my screen?
Yeah, I can see your screen.
And also my voice is okay, right?
Voice clear.
Okay,
Everyone
so
clear?
yeah, throughout the presentation, if I talk too fast or that you have any question or something like that, just feel free to let Azri or the other people knows about it. And actually today I am supported by Mr. Loy and Mr. Teoh, who are both also the specialists for XRF and XRD specialists in our GS Corporation. So let me give some brief introduction about RGS Corporation. So RGS Corporation is actually founded 12 years ago. So even with that, Mr. Teoh and Mr. Loy themselves, actually they have more than 20 to 30 years of experience in servicing and also the application part for the Rikaku. So our main business for RGS Corporation is actually the distributor for this Rikaku, who is specialized in X-ray and also the other instrument. So actually for us, right, we actually have 4 locations in Malaysia. The HQ is actually in Sri Kembangan, which is very near UKM. And we also have a Ipoh office and also Penang office. as well as one in actually Kuching and also Bintulu. So actually our specialist is actually throughout the different part of Malaysia. So even you are from Kuching or from Penang or even from Bintulu and so on, we actually have people to support you for your servicing and also application job. So actually this is actually our organization sales chart, and also this is actually our service and application. So Mr. Teo is actually our technical advice, and also we are supported by Dr. Firdaus, who is actually the lecturer from UTM. So Dr. Firdaus, he's mainly focusing in the XLD. So if you guys also have any XLD question, then feel free to contact us as well. So what LGS specializes is actually in elemental analysis, and so XLD thermal analyzer, and also we're also distributing NMR. This is actually a benchtop NMR. The benefit of this NMR is actually it doesn't require any liquid helium or liquid nitrogen, and the maximum it is actually 80 megahertz. So which is actually very good instrument for screening and so also teaching purposes. We also have spectrometry and also imaging system. So this is some brief introduction about LGS. And next, let us introduce about Rikaku. So the Rikaku is actually in Japan. It's actually a Japan company. So the HQ it is in Tokyo, and also they have actually another one is Yamanashi factory, and also as well as the Osaka factory. Most of the actually the XRF manufactured in Osaka plants. So beside XLD and XRF, right, they actually Rikaku also have quite a lot of different range of product, inclusive of XLD and EDXRF, small angle X-ray scattering, which is a dedicated SAX machine that is also part of like a spin-off from the XLD. And we also actually have a single crystal and lip system for elemental analysis, and also thermal analyzer TG, DTA, DSC, and so on. So even though it is actually not so famous in Malaysia, but Rikaku thermal analyzer, right, is actually the #1 selling thermal analyzer product in Japan. And also we also have a single crystal as well as other semiconductor equipment as well. So probably not everybody is very familiar with Rikaku XRF, but nevertheless, right, they actually have a very long history about the instrument. So the first actually XRF was the launch in 1962, and throughout the years they also improved a lot of different technology. One of the highlight of the product is actually a tilt above industry, tilt above WDXRF, which is actually solving a lot of problem of sample leakage and powder dropping into the chamber and so on. Later on, we actually going to further introduce about this product and also why it is very, very good. And also on year 2020, they launched Primus 4i. Okay, one thing about Rikaku, all the floor type WDXRD, they actually named it as a Primus, but different Primus series. So on 2020, they launched the Primus 4i. So this is actually not a replacement for the Primus 4, but it is actually a product which more suitable for oil and gas industry. As far as even though actually tip above is actually a very safe instrument, even for the liquid sample, but the sample preparation can be more complicated compared to the tube below XRF system. So that's why they launched this Primus 4i with a tube below design that is actually dedicated for this what you call that oil and gas or liquid sample customer. So we always advise customer if they actually 90% or 80% of their sample is powder, press pellet or fusion, by all means get the tube above system. But if it is the other way around, then we will recommend a tube below system. Okay, so this is actually the kind of like the summary of what the product is. There we have actually, this is a floor type WD system, which is can be 3 kilowatt or 4 kilowatt. We also have this is a benchtop system, which is a 200 watt, and this is a simultaneous WDXRF. So it is actually very dedicated for industry where what they're measuring is actually a very specific element, and they want to have a very fast measurement. Also, there is actually a micro Z and mini Z, which is actually also an industry model where they only want to measure one or two elements in the WD. And of course, we actually have an ED system. And worth to say, right, now we actually have a second generation Next CG2. And then UPMM just purchased this instrument, and then we are actually going to deliver to UPMM soon. So this is actually the outline of this today's presentation. So the presentation is going to like divide into three different parts, where the first part, which we are going to talk about XRF theory, hardware, qualitative and quantitative analysis. And also second part is actually a sample preparation. And the third part is going to be like the application available in UK and the possible future upgrade. So in here, I'd like to mention that the first part, there's a lot of theory and also a lot of hardware information and also like qualitative and quantitative information. This is more like for your information, because a lot of people like they might be using the WDXRF and so on. They were talking about that they are using the standardized analysis and so on, but they might not know quite well, or they might not know it how it is being done. So in here, as far as it might sound really boring, and also sometimes some of the information is a bit hard to remember or so on. But by all means, you don't really need to remember all these things or understand all these things, because nowadays, right, the software and also hardware technology mostly automizing like 90% of the work. So even we as a specialist in RGS, we don't really understand some of them, how they work in the basic. Okay. So the first part, right, is going to be like a review of basic XRF theory, wavelength dispersive, and so on, and also quantitative, qualitative method, and also what influenced the trace analysis. So I guess quite a lot of people in here, right, they have some exposure of the XRF and also X-ray, basic X-ray theory. So in here, I'm gonna like slightly briefly go through it. So what is X-ray? So X-ray is like actually is an electromagnetic wave, which is similar with what we have seen day to day, like the light. Light is also an electromagnetic wave, just that actually their wavelength is actually longer. So what you can see is like the visible light is around 6, which is a very narrow range. And of course, we have a microwave, which is what we use every day to heat up our food. So on the shorter wavelength itself, right, we actually have this region itself that you can see 2 and 3. This is actually considered X-ray that we are using for the analysis. So this X-ray itself, right, if you are not actually familiar with the XRF analysis, but you sure will know that X-ray is being using for the imaging. So imaging itself, right, what we go for hospital for like the chest X-ray, this is also using this part of the X-ray. So in short, right, X-ray is just a part of the wavelength that we actually see day to day. So characteristic of X-ray, when actually X-ray hit a sample, it actually have a different type of influence, like photographic effect, that is a chest X-ray, scintillation effect, which is also what we using this as a scintillation counter, and ionization effect, which you actually we using for proportional counter. So in here, right, this is actually two very important phenomena that because we are using this phenomena to detect the X-ray. Subsequently, this is make it possible for the counting of WDXRF analysis. And also that actually we have another effect, which is a diffraction. This is another very big topic that we can also talk about in the future. And also that penetration depth is actually going to be different according to the different type of sample. So this is actually kind of like what happened when the X-ray hit the metal. So inside, actually, there are generating a lot of, when the X-ray hitting the sample itself, right? not only it is generating the fluorescent X-ray. This is what we're using for the WDXRF analysis, or even EDXRF is also using this one as one of the things to analyze. And also we have a lot of photoelectron effect. Most of the X-ray is actually generating and it's going to convert into heat. That's why when you using WDXRF or any X-ray technology to measure the sample is going to heat up the sample. And also there are some X-ray which is transmit through the X-ray to the sample. So this is actually what we're using for the X-ray imaging. So if you're actually doing the X-ray imaging, the X-ray generally using is actually a shorter wavelength, so which they have a higher energy. So another two effect, which is a Compton scattering and Thomson scattering. This is kind of like considered as a noise, but nevertheless, this information also can beneficial for the WDXRF analysis. So then come to the principle of WDXRF. So why it is actually possible to use this technology to measure the elemental or quantify the elemental? So when the X-ray tube generate X-ray hitting the sample, it's actually going to consider generated the fluorescence of X-ray. So where is this fluorescence coming from? So this is primary X-ray. This is actually from the X-ray tube itself. So when the primary X-ray hit the electron at the different shell, so it's going to excite the electron on different shell. Subsequently, it's going to kick out the electron as a photoelectron effect. So imagine when you actually have the electron being kicked out from the K shell, the L shell, automatically they actually tend to be going into the lower shell. So in this effect, right, by doing so, they actually need to give up certain energy. So this energy giving up is actually generating the what we call that the fluorescence. So when you actually from L drop to K shell, it's actually going to consider as a K alpha, and also from L drop to this what we call that K shell is going to be K beta. So one of the very important for the WDXRF, what we always talk about is actually K alpha, K beta, L alpha, and different type of things. So this is the energy signal that we are actually detecting in the WDXRF or EDXRF, because all the element itself, they will have a specific and unique energy level. So which make it WDXRF or EDXRF possible. So what can we see in the XRF is actually qualitative and also quantitative. So actually, as you remember just now, what I mentioned to you, different elements actually generate different level of the wavelength. So this is actually why there is actually unique signal at here that we makes it possible to measure to identify the signal. So what people always talk about EDXRF and WDXRF, what are the different things? So it's actually very simple. In the WDXRF, you have a crystal, and you actually have a detector and also sample and X-ray tube. So in WDXRF, right, how we separate all the signal, because when actually X-ray hit the sample, all the signal is going to come out simultaneously. So the crystal itself actually doing the work to choose which signal can be seen from other detector. So by satisfying this Bragg's law, this is the same laws as what we use in the XRD, except in the XRD we are measuring the d-spacing, and in the XRF we are measuring the lambda. But in the EDXRF, there is no crystal in here. So what we are using in the EDXRF is a very sophisticated detector, which can separate all the signal. So that's why we actually say one of the advantage of the WDXRF is the detector you don't need to change it at all, because actually it is all the work itself, right, is being done on the crystal, and the crystal never spoil. And the detector theoretically it also never spoil. So even though the starting cost for having the machine itself is higher, but throughout the long run of the whole machine itself, right, you actually saving a lot of cost, because the detector of the EDXRF, the cost can be 1/3 or even 1/2 of the whole instrument. And this is actually because it is a semiconductor detector, and it actually have a lifespan about 5 to 6 years maximum. So why we people like to using this actually what you call that XRF? Because it is actually a very simple in terms of sample preparation compared to ICP and AAS or the other chemical analysis method. Anybody who actually we just go through the training, they can prepare the sample very nicely. And also the cost of measurement is very low, and the total measurement time is analysis time is very short. And also, I think probably one of the most important part is actually the wide dynamic range of measurement. Even though you say in here is ppm, actually a flow type WDXRF can start the measurement from ppb to 100%. Compare with actually, let's say ICP and AAS, yes, theoretically, you actually can measure from ppb all the way to 100%, but there's a lot of dilution to be done. So the disadvantage of those wet chemical analysis is actually, it is very easy to generate a lot of human error. So that's why in terms of industry, if possible, most of the people actually prefer to change to WDXRF or EDXRF for the thing. So it actually can be using for qualitative control, process control, research and development, and screening. So most of our customers actually in the research and development and also quality control. And then screening itself, they prefer to use more like handheld EDXRF, so which is also available in RGS Corporation. So this is actually the industry that is possible to use in the SRF: electronic, chemical, ceramic, mining, petroleum, steel, non-ferrous metal, environment, and others. So pretty much every industry itself, right, that it is possible to using the XRF, because XRF itself, right, is actually a very dynamic instrument that as long as you want to know about the elemental content, and then it is possible to do. Of course, in terms of, let's say you really looking for very trace of elemental content. So ICP or the other things is still the preferable option because they have a higher accuracy in terms of the ppb analysis. So this is actually some comparison between WDXRF and EDXRF. So one of the very important part is actually the spectral resolution. So the best EDXRF, I think, probably can reach about 130 EV. Meanwhile, compared to actually WDXRF, our can very simple achieving this 26 EV and so on. So which is important when you want to do mineral, where there might natural mineral, they might have a lot of element things which is overlapping each other. So you got to have a very good resolution to separate those very closely related peak. So the WDXRF is still preferable. And of course, the precision is very high, and also maintenance cost is very low, and so on. So it comes to the part about understanding what is inside the WDXRF. So that doesn't matter which maker you are actually going through, like, and so on, or even the benchtop or flow type. Mostly, they are actually the design of the system itself is actually still the same. You are still going to consider having an X-ray tube, and also the primary beam filter, and sample holder, diaphragm, attenuator. This is actually simulation counter and proportional counter. This is the tool detector, and also analyzing crystal. So the main component in the WDXRF you can actually think about is only 3 parts: X-ray tube, detector, and crystal. So this is actually the whole thing's actually driving the whole WDXRF, which is making it possible. So in here, below, we are going to talk about slightly each of them so that you can more understanding about this instrument. So in terms of first is actually the X-ray tube. So this is actually X-ray tube which is makes it possible to generating the X-ray. So X-ray tube you can think about is actually as a light bulb. Basically, it is also can be considered as a light bulb, where you actually have a filament, you actually have a target. So depending on what target you are having, that can be rhodium and it can be copper and something like that, depend on the application. But mostly, most of the flow type WDXRF, they are using rhodium, where else like the benchtop, they are actually using, we are using platinum. So three things actually to be actually important for the actual tube is actually the tube voltage, which is generating the excitation energy. So the excitation energy determine which line you actually can be generate, either is K alpha or L alpha and also so on. And also the tube current itself, right? It is actually proportional to the X-ray intensity. So if you want to have a higher intensity in terms of your the count, then you can actually increase the tube current. And also another very important part is actually more important part than actually tube current is actually the window, because actually the tube itself is designed in the vacuum or in the gas, where so you need to maintain the system in the vacuum. So this BAE window, it is actually a very light element that allow the X-ray to passing through without absorbing a lot of energy from the tube. So a thinner X-ray tube itself, window itself actually can provide more X-ray intensity in compare where you increase the tube current. And also because when you increase the tube current, it's going to generate a lot of heat. So in the X-ray tube itself, right, generating X-ray from the electron is actually a very inefficient process, where meanwhile most like 99% of the energy is going to convert into heat. That's why we actually need to connect into the external chiller to remove all this heat. And the second part is actually the primary filter. The primary filter itself, right, actually is the work is actually remove the background and also to improve the measurement capacity. And also another very important part for the tube below system is to prevent for the debris from the sample to drop on the tube itself. So in the tube above system, this is not important because it is quite impossible for the sample to drop to the detector crystal and also even for the X-ray tube. But for the tube below system, when the sample drop onto the tube, it might damage the tube. Then the subsequently is a very high cost to replace the tube. And of course, in the system, we also have a different filter like nickel filter for 440, aluminum, and so on. So in the modern system itself, right, the software will automatically determine which is actually the filter to be used when you want to measure different elements. So you don't really need to remember by heart. Meanwhile, if you're actually talking about 10 years back, so on, the specialists will need to remember which filter to be used for every element. So which makes it very hard for the day-to-day people to actually create their own measurement program. So another part is actually a diaphragm. Diaphragm is actually limiting what is actually the X-ray beam size actually beam can go into the detector. So if your sample is actually, let's say you are using the 30 millimeter diameter sample ring, so you will need to choose about the 30 millimeter diaphragm. So it's actually related to which is actually the sample holder that you are using. If not mistaken, in UKM they have a 10 millimeter, 30 millimeter, and also 40 millimeter. So why we have a different type of size is actually depend on your sample size. If your sample size is very small, then you actually can using the 10 millimeter, or your sample is actually quantity is a lot, then you can actually use a 40 millimeter. So in the software itself, you can choose the different diagram, so and so on. And also, one thing actually, the X-ray itself, right? As far as you might think, actually, that the stronger intensity is actually at the center, but it is not. It is actually slightly shift to the left-hand side. So the hardware itself will actually automatically design in a way, right, to maximize the actual intensity go into the system. And also in the measurement, we also going to rotate the sample so to make it more homogenized when you want to do the measurement. So another one is actually the attenuator. So the attenuator function itself, because actually the detector itself, they actually have a limited count, how much the count actually that can go into the detector without actually how to say saturate the detector. So what happens is actually saturating the detector is it's not likely you are going to actually damage the detector, but what is problem is actually when you you're having a saturation, the X-ray intensity doesn't increase when you actually concentration increase. So that's why we actually can put an attenuator there to prevent this from happening. Of course, you can actually say you can decrease the current going into the system. So in the modern system, right, what we are trying to do is actually to not to adjust the tube power too much, because actually adjusting the tube current itself actually it create the instability in the measurement system. So it will take some time for the tube to become stable, the current to become stable. So this is actually kind of the last option that we are using. That's why we're actually using the attenuator, which is a hardware in terms of to reduce the X-ray intensity. Another one is a solar sleep. Solar sleep is quite important as far as compared to a lot of other people. That solar sleep itself, right, is actually just I skip a little bit in here. So solar sleep is actually just a parallel plate, because the X-ray when you're coming up from the X-ray tube itself, right, the beam itself it is actually not parallel. It actually is going different direction. So this solar slate itself is actually going to limit what is the beam going into the system to make it kind of say resolution to become a better. So in the system itself, there are few different type of slit which is available. So what you can see the effect of actually in here, that you can see the resolution become different when you're actually using the S2, S4, and so on. So theoretically, we want to use the to give a better resolution. It's easier to using a very thin solar slit, small solar slit. But what is the sacrifice? Is actually sacrificing the intensity. Whatever we do in here, right? We actually want to maximize the intensity and also how to say, giving you the better resolution. So analyzing crystal, which is this is a very important things. So this is actually as long as actually the beam going to the system can satisfy this Bragg's law, it actually get diffracted. So this is actually how the system select which X-ray to go into the system. So in the system itself, right, actually in the Primus 4, you can actually put up to 10 crystal, and then the default actually given is 4 crystal, which make it possible to measure from foreign all the way to cm, if not okay, cm. And also it is possible to adding you actually can starting from measure from oxygen all the way to cm. So and also that if in the future if needed, it can be added different count crystal. And also the other one is the detector. There are two detector in the system. One is scintillation counter, another one is proportional counter. So scintillation counter is actually measuring the heavy element, where the proportional counter is measuring the light element all the way to SC. So it covers the both end. So both the actually scintillation counter is actually like a light counter itself. How it works actually when the X-ray go inside, is going to bounce along in this photon multiplier tube in terms of it creating a pulse in here, as well as the proportional counter is also generating a how to say a pulse from the wire in the central wire in here. So both they actually contribute to the counting of the X-ray. So in here, PHA itself, right, is quite a little bit hard to understand the concept, but the main thing is actually, it is actually limiting what is the energy that can go into the detector. So by saying so, like, if you look at here, right, PB and also SN, actually their wavelength is actually, this is actually a double of this thing. So if you don't have a PHA, right, you are actually going to detect both these things at the same time. But what the pulse height analyzer do, right, it limiting only this energy can go inside there. So, and then because this SN actually have a high energy, so it doesn't allow it to go through into the system, that you don't create a double count in the system. So this PHA is very important, and then normally is a default set by the factory, and also of course the user can adjust it accordingly. So this is actually the hardware part. Where it comes to now, another one is actually the analysis. Okay. I think I'm gonna run a little bit over time. Should be quite over time. So I'm gonna go a little bit faster in here. So in terms of XRF analysis, right? There are two analysis. One is qualitative analysis, another one is quantitative analysis. So most of the people using for the XRF analysis, they are mainly more interested in the quantitative analysis, whereas qualitative analysis is kind of like looking at the thing. Nevertheless, I'm going to talk a little bit about qualitative. So qualitative, as what is suggested, it just allows you to see what is the element inside there. It doesn't convert into the doesn't convert into the percentage. So when you actually want to do this, if you only interested to do a screening, then you can use the qualitative analysis. And for to quantify the things, right, there are actually two different ways to do it. One is using the empirical calibration, and the other one is a standardless method. So as what is suggested in here, right, quantitative analysis, empirical calibration, meaning you will need to have a standard to calibrate. So it is very important that you having a good standard, and also the standard itself need to represent what you want to measure. You cannot say I giving you let's say a sample which a standard doesn't contain sodium, then you want to measure sodium, which is impossible. So it comes to the part where to get the standard, which is if there are a lot of international standards available worldwide, but unfortunately they are very, very costly. So which makes it very difficult for people where you want to actually, if you only not a production or not a manufacturer, you want to buy a standard, it's very costly. So the second way actually of doing it is actually by having a secondary standard where you actually can send your sample to ICP, and then from there we can actually generate the standard in terms of calibrating the system. So put it this way, XRF analysis, it is good when you want to do quantitative analysis. Empirical calibration method give you the most accurate result, and how accurate it is, the calibration, it is actually your standard. And of course, there are actually a lot of effect which is actually contributing into the arrow. So one is actually the matrix effect. The matrix effect is actually what the element inside that can affecting the element intensity. So that's why we actually have another section which is going to talk by Mr. Lloyd to talk about the sample preparation part, because what sample preparation part actually can very well eliminate the matrix effect and so on. And also, as what is suggested in KC, you can see, right, the cadmium in here, it is also on these 4 different type of medium. aluminum, copper, polyethylene, different thickness, you can see the intensity itself is actually not a constant, even though all of them contain about 100 ppm. So it is actually affecting by what you have inside the system, that this is not a constant value. So that's why it is very important that you are actually using the standard which is similar to what you have in your sample. And also the thickness where it actually can, penetrate, it also depends. Generally speaking, we actually say the light element itself, right, allow the highest X-ray to penetrate, the X-ray to penetration depth is actually higher, where you actually have a high Z medium, the penetration depth is actually going to be very, very small. And also there is also an absorption effect, and also absorption and also enhancement. So in general speaking, right, where the Z value is actually 2 positions higher than your element, is going to it is actually going to enhance. Like for example, this one is actually the Fe is significant absorb the nickel, and then the Fe intensity, it is actually going to actually enhanced by the nickel wavelength, where you actually have the other way around, where you have a chromium with Fe is going to be the other way around. So it becomes a different type of effect. And also there is actually, with all these things, right, so there is actually a lot of things to think about. How do we understand to get the true intensity is by using all these so-called matrix correction. So there is actually a formula in here. This is actually how the formula works, that you have really, if the true index concentration and also calculated concentration is equal to 1, where there is no matrix effect. Where this true value and also calculated value of the concentration is different, then there is so-called this matrix effect, which is contributed by all the other absorption, enhancement, coexisting element, and so on, and a lot of the things combined together, and also the penetration depth. So this is a formula. It sounds very complicated, right? Yes, I think it's very complicated for me to understand about it. The good thing about all the premise system itself, right, there is also automatic correction program in the system. So which is already built in. When we choose it, it will actually automatically determine what is actually being absorbed, what is actually the coefficient. And this coefficient is actually this number. This is the coefficient. So the software is actually automatic, will calculate the coefficient according to different type of element that you actually have inside the system, and also actually and also automatically calculate the and makes it possible to the true concentration, true calibration curve in here. So just previously we talked about empirical calibration. So which means you actually need the so-called standard to do it. Another one is very important, is actually fundamental parameter, which is what we also call it standardized analysis. So standardized analysis, right, is based on some assumption, and what it does, right, is it gives you the possibility to measure the sample without having the proper standard, but based on some assumption. The elemental are distributed homogeneously in the sample, which is very easy to do. We actually can just mill the sample and also press it, and also do the fusion or something like that to eliminate this process. And unmeasurable element composition, for example, carbon, hydrogen, oxygen, even though we say we can measure oxygen, but normally people don't measure it, and also carbon, hydrogen, and also nitrogen. So we actually need to know what is actually the composition in here, or then we can manually key in this result, or we actually can using some Compton scattering to estimate. And also there are some other in here. So in the Rikaku software itself, right, they actually, when you want to do the standardization, they will actually ask you about this sample preparation information, which is very easy for you to do because all these things you can get is a physical things that you actually can know from outside. And what it does, right, as far as it mentioned in here, right, we actually can say the intensity coming out from the system is actually the primary excitation plus the secondary excitation, which is what we actually doing in the previously. And then we can plug in the formula to calculate what is actually the intensity. So what it does, right, is actually doing the measurement of the actual intensity, plug in into the formula and convert it into the percentage. And how it do it, right, is because we actually have a measurement intensity and we also have a calculating intensity. What the software do, right, it actually compare these two parts. If the estimated calculate intensity match the measurement intensity, it means that this two system is matching. Then we can actually give you the analysis result. If it is not matching, they actually can adjusting the theoretical intensity calculation formula and re-estimate the composition and check it again. If matching, then this is the result. So in short itself, right, semi-quantitative or SQS analysis is actually a method to compare the calculated result as with your measurement result. If people who is actually familiar with XLD and familiar with rate-well refinement, the concept itself, it is actually very similar. Where in the XLD, you will actually have a calculated intensity and profile compared to your measurement profile. So this is the same concept. In the Rikaku software, right, another thing is actually, because normally when we're using the standardized analysis, and even though it's actually called a standardized analysis, but it actually has so-called a common library, which is a pre-measured intensity inside the system. So the system itself, right, when it calculates, it using the common library. But in the Rikaku software itself, right, it actually can have an additional standard where you actually can input so-called a matching library to improve your measurement, improve your standardless calculation according to the standard that you put inside there. Meaning that you actually can have just one or two standard to put inside your system to improve the standardless analysis. So this is actually the quantification part of the system, where you actually have an empirical calibration, and you also have a standardless measurement. So another one is actually the trace analysis. This one I actually I talk a little bit about it because I think a lot of if people from the research and so on, somehow you might be interested in terms of you want to identify what is the trace amount in the sample. So the trace amount is actually first is depend on actually what is the medium you have, as what you can see just now previously. If you actually have a very light element, that your penetration depth is actually going to be lower and also your intensity is going to be higher. So which means in this sense, you actually can detect a very small amount of the sample, a small amount of the trace element which you are interested in there. So as you can see in here, in the polymer, you actually can detect up to like 1 ppm. Where you have a iron-based sample, then you can actually the minimum amount is actually what you call that 100 ppm or even 200 ppm and so on. So this is actually one of the very important factor for how low can your lower limit of detection, which is what LLD stand for, can go through. So if you actually you can have a piece of metal, you want to identify the light element like sodium inside the metal, which is going to be very difficult because the detection limit is going to be very high. And also there are a lot of other things where we can actually improve the sensitivity. One is actually the tube condition. In here, what it means actually we can increase the tube current, meaning actually you can go to higher current to improve the intensity from there. Generally speaking, kV itself doesn't contribute much to the intensity of the system. So increasing the kV itself doesn't really help too much. As you can see in here, this SR is actually 29 ppm. That increasing the kV doesn't change too much. Like from this one, the PV ratio is actually 1.07 to all the way increase to 60 kV. It is actually only increase a little bit. Where else actually you increase the this is also the voltage. So it just means like it doesn't improve much in terms of the voltage. The intensity doesn't increase much in the voltage. Another one is a primary filter. So as what I mentioned to you just now, the primary filter itself actually can remove the background. So in the system itself, it automatically determines what is actually the filter to use. And when you want to measure cadmium itself, right, the system will automatically pick this filter. Then you can see that the cadmium peak is very obvious. Is very how to say, is very obvious in here. Then where you are compared with no filter at all, where you cannot see the cadmium peak. As well as this one, this is another example to suppress this continuous action from the tube. Then you can see this XR in here. And the divergence slit. So divergence slit is actually improve the resolution in track of the intensity. So if you want to identify these two elements, V and Ti, so you will need to use this S2, which give you a better resolution by sacrificing the intensity. So if you actually using the S4, which is actually a higher slit, it's a bigger slit, then you actually don't have the good resolution to separate all these things. Another one is actually very important, is actually what crystal to be used. So some of the crystal itself, right, it actually can significant, in this table itself, you can see, it actually, some of it is good, but some of it is actually better, and some of it is excellent. So by saying all these things, right, that if you're using lift, you actually can get some good for the mineral, for some heavy mineral. And this is an example that you can actually see compare the lift 200 to lift 220. This peak itself is actually more obvious in here. The resolution is going to be better. And in the Primus 4 system itself, right, it will automatically determine what is actually the crystal best for you to use it. Of course, you actually can choose it according to your different need and so on. Okay. At the end, right, this one just now we talked about it. What is the strong point of XRF and what it can be used. Another thing is actually important to know about this accuracy and precision, where you actually in the industry, in the analysis, especially in the industry people, precision of the measurement is more important than the true value. If you have a very good precision, you can always adjust to make it reflect the true value. Meanwhile, actually, when you have if you have what you call that, poor precision but very close to the how to say, or the true value, it might be very hard for you to control the process. Later on, Mr. Lloyd is going to talk a little bit more about this part. And why we are saying this thing is actually, I want to bring out, this is the table. So arrow which is contributed by the spectrometer, like for example, statistic count, counting loss, stability, actually tilt, and electrotechnic ball overlap temperature characteristic. it is actually very easy to control, which all the XRF system itself, it actually already minimize a lot of this part. One of the very, very important, which is contributing to the error of the measurement, is actually the sample preparation. So that's why the next part is actually where we're going to talk about the sample preparation, which is contributing to mostly, I would say, 60 or 70% of the sample measurement. So even though we say that actually WDXRF sample preparation is very, very easy in compare with the ICP and so on, but a good sample preparation also actually will ensure that giving you a very good measurement result. So yeah, this is actually the end of my presentation. Yeah. So I will pass the time back to Mr. Azuri. So yeah.
Okay. Mr. Kelvin, is sample prep method you cover?
Mr. Loy.
Okay. So this will be your end
Yes.
presentation lah.
Yes, correct.
Okay. Okay, so now I open for question. So if you have a question, you can ask in the chat box for Mr. Kelvin or our lab. Or maybe if you like to talk, you can unmute your your mic and then ask directly. Okay, question from Mr. Kian Long Lim. What is the expected sample size to get a reasonable and reliable result?
Actually, we would like to say as your sample as big as possible, quantity of a sample is as big as possible. But if you actually if your sample size is actually very limited, the advantage of UKM system that they have actually a micro mapping system that it can be using for even you have a microgram or sample, you can still possible to do the measurement. It's just that if this is kind of the sample, your sample quantity is a problem, what we also always can do is actually lengthen the measurement time. So which make it possible to get a very good result.
Okay.
So I think the smallest that can go for the gram can be microgram or 1 or 2 gram. Micrograms should be still possible to do. And then the sample size, because the smallest bin it can go is 1 millimeter. Yeah.
Okay, question from Azharin. Can carbon be detected by this equipment?
Okay, this equipment that actually, if you go for it, you can actually see there is a carbon crystal RX61. So this system can be detecting carbon provided they have this analyzing crystal. And then unfortunately at this moment, this UKM system doesn't have a carbon crystal. So if actually, I think if the demand itself is very high, then we can also think about is that economic wise to increase the include this carbon crystal into the system. So, and also one thing is actually depend on what kind of medium you want to detect in the where your carbon is content. For example, for the because actually for this BEB and also carbon or this very light element, you can say starting from fluorine, the sample has to be in the solid form. You cannot actually detect in the liquid form. Because actually one thing, as much as we don't talk about it, the system need to be measured in the vacuum to detect the foreign MBE all the way to foreign. Because air, even we can use air, we can use helium. All these actually medium itself that also absorb the X-ray. All these very ultra light element there is very easily affecting by all this medium. So if your sample itself, it can be pressed in the heart in the solid form, then we can run the measurement in the vacuum, then we can detect when you're having this crystal.
Okay, from Chin Kok Yong. Hi, we are interested to scan bone, which is the most organic sample with uneven surface and size. Do you have any experience with this kind of sample?
Okay, actually, because the 1 millimeter is actually the smallest bean size, so it can be put into you actually can just polish because the sample surface relatively to 1 millimeter, it is actually quite flat. So depending what kind of bone, if you give me a chicken bone, when it's very small, it's going to be very curvy. Like when you actually take a very bigger bone size or something like that, it will be relatively flat. And we would need to know what you would like to measure in the in the bone. Is a red bone can polish? Then it is possible. So in this, because bone itself also a lot of calcium, right? Calcium and yes, it shouldn't be any problem. So actually in the third section where we're going to talk about the application. Sorry to bore you guys for the last 1 hour because this is actually how to say fundamental of XRF where we don't really talk much about application. In the third session where we're gonna talk a lot about application and what it can be done in the UCAM system. Yeah. So yeah, to answer your question, it should be all possible to do it.
Okay, I think that's all because we have a limited time. So after this, we will take a break time.
Maybe we can shorten the break time.
Maybe we can start back at 10:20. Is everyone okay? Can you give me your feedback on the chat box? Okay, 10:20. Okay, so everyone okay. So before we have a break, I would like to share with you our current promotion. Okay, Sharp slide. Okay, if you look at the poster over here, we are now giving you a discount on our service analysis, 10% discount and 20% discount. 10% discount is for UKM client, and then for 20% discount for non-UKM client. Okay, but bear in mind that this promotion valid until 31st of December only. So if you would like to grab this promotion, make sure you submit your form to us not before, last 31st December. Okay. Thank you. So we will come back at 10:20. So our second presenter will be Mr. Loy Hao Chi. Thank you. Okay. Are you guys ready for second slot? Okay. Only one person ready, Mr. Abdullah. How about other guys? Okay, Mama Faizun ready. Cik Abuzar ready. Dr. Nurul ready. Angeline ready. Zalina Laili ready. Lady Hernando ready. Okay, everyone is ready. Okay, now I would like to invite our second speaker, Mr. Loy Hao Chi, Senior Sales Manager from RGS Corporation for our second webinar. He will cover on sample preparation method and some application sharing lah. Okay, so this is a brief biodata of Mr. Loy. He is a Senior Sales Manager from RGS Corporation Sdn Bhd. He obtained his honor degree in Electrical and Electronic in year 1996 and start his work as a process engineer in a semiconductor company in 1996. He has 20 years experience in semiconductor, cement, oil and gas, geological, especially for analytical X-ray technique, spectrometer and scanning electron microscope and others analytical equipment. Okay, in year 2011, he moved to RGS Corporation as head of department of sales department, where he was responsible for analytical equipment for various field and application. So now I will give Mr. Loy. Mr. Loy, ready?
Okay, thank you. Yep.
Okay.
Okay, thank you, Azuri. So thanks everyone and thank you UKM for giving us the chance today to share with you these webinars. So today on my parts, I will share you about on the XRF fluorescence on the sample preparations things. Okay. So can everyone see my screens? Okay, so without further ado, then let me start the presentation for today. So, okay, so today my main will be talking about the sample preparations, especially on the X-ray fluorescence analysis. Okay, so as Kelvin mentioned earlier, in XRF analysis, there's a few factors that going to affect your analysis results. In overall, we can split it into part A and part B. So A will be mainly attribution for by the spectrometer itself, means by the hardware. But as what we mentioned earlier also, actually the main error factors are mainly coming from your sample or sample preparations itself. So few of the main things that going to affect your sample analysis result or giving you error in your analysis result. The first thing will be the heterogeneity of your samples. Okay. Then secondly will be the unevenness of the sample surface. Third will be the grain size and also especially for the powder samples. And also your polarizing methods. Okay. Then the fourth will be coexisting elements contained in the samples. This is something which also I think Kelvin did explain about that just now. And number 5 will be the nature of samples, especially something like moisture absorption characteristics, or if the samples is dry at one day and is wet on the day 2 or in the second kind of measurements. So this will give you errors. And the number 6 will be the accuracy of the chemical analysis. So means from the reference value which you get from other measurements, maybe like a wet chemistry analysis or ICP or fire assay value, is that value accurate or not? So all this is contributions to the errors of your measurement results. Okay, so I think this is the same thing which also we will talk about, or Kelvin talk about. So we got accuracy and also we got precisions. So if we have a very good accuracies, but we have a very poor precisions, that's also not really is a good measurements. In the best, what we need is a good precisions and also a good accuracy. This is something that we always aim for. Okay, so the first thing, point of sample preparation. Why we need to prepare our samples? Okay, why we need to prepare our samples is to ensure that we can get, the homogeneous of the samples. We can ensure that all the samples are homogeneous and there's no difference from point A and point B, which will give you a different measurement results. And secondly will be the consistent preparations procedure. So your procedures must be consistent. So this means that if today, for instance, I'm doing the preparations and tomorrow when Kelvin are doing the preparations, we must follow the same SOP where there's no big deviations or difference from our preparation procedures. Because the different preparation procedures will give you a different results. And I think somebody was asking about the sample size just now in the chat. Okay. For instance, if we are doing a powder measurement, when today you are doing a powder measurements for powder samples of 3 grams or maybe 5 grams, and tomorrow you try to measure it with the 2 grams or even 1 grams, this will give you errors in your results. So your consistency of your measurements will not be there. And the third, and one of the very important, is try to avoid contaminations. This is important, especially when you try to do trace analysis in your samples. So especially when your trace analysis, your trace materials or elements is very low, and this might and you're using your containers or your sample preparation tools are not clean enough, this will give you contaminations or give you some unwanted elements inside your measurements. Okay. So first thing is about steel and metal samples. How are we going to prepare if we are trying to measure some steel or metal samples for your XRF? Okay. So the very important thing which we were talking about is that the measurement surface need to be flat. So when we say about the measurement surface need to be flat, means that normally if any steel or blocks or metal blocks, to make the surface flat, you need to polish it. So during polishings, we either by grindings or by sandpapers, belt surfacer, or even by latings process. Okay. For different materials, we are using different methods or different things or methods or different materials to make sure the surface is flat. Okay. So once the your surface is already flat, then you can process for your analysis. But during this process or during this polishing process, actually this will also contribute contaminations into your samples. For examples, okay, this is the influences of the polishing roughness. Okay, first thing is the roughness will give you a different influences. If you use a different grain size of polisher, then you can see that your nickel concentration is getting different. And your chrome also is getting difference from every different roughness. Okay, if you can have a very nice mirror polish, then you can have a very, much more better results. But to get the mirror polish every day is it's very lengthy, it's very difficult. So most of the time, I think that's why we need to tolerate in one of the results which you think that is suitable or you are acceptable for that, then you stick for that. For example, if day one you are using 240 emery papers to polish your samples, then you should use this as your standards. Then every of the samples should be processed by this grade of sandpapers. Then beside that, the polishings also from the emery papers, it will contribute some contaminations. Okay, especially let's say from your emery papers, it will give you a certain levels of contamination into your results. For instance, nickels actually is 0.5% are contributed by the abrasive belts, and chromiums is about 0.03, and Fe is by 0.38. So beside getting your surface is clean or flat, also actually your abrasive materials is also will be enter into your samples. This is something that you need to aware of during your sample preparations. Okay. So secondly will be about the granule or powder samples. So normally this kind of samples will be coming from either it's a geological samples or some kind of your synthesis materials or even biological materials like bones, teeth, kind of things, or even branches or leaf from the tree. So this is all can be categorized under this. Okay. So for this kind of samples, the important process that we normally recommended to do is to dry your samples. You have to ensure that your samples is dry, and this I think should be also consistent. Okay, so once the sample is dry, then you need to process by grinding. So grinding is we recommend that to actually to reduce the grain size effects. So we need to control the ground size. So normally we recommend the things to be less than 50 micron size. Okay, so actually after grindings, then you have to feel that the powder, your samples is very smooth. Something like you are feeling in your talcums, okay, your body talcums, your baby talcums, is that kind of smoothness. Okay, this is for XRF. So, but in industry, a lot of times, people are controlling by using by sieving. So means after they grind the samples, they pass through sieve to ensure that all the samples that they collected can meet this 50 microns or below the 50 micron grain size. So after you have powder samples drying and ground, so the next thing is we can either process with loose powder measurement, but normally we would suggest you to go for a pressed pellet. So because by pressing the samples, we can increase the density of the pellets or your samples. It can give you a much more accurate results, or you can even detect some light or even some trace elements inside there. It's really the light elements. But if your samples is very difficult to form a bit or a pellet, we call a pellet. So this is the time that you need to mix your samples with binders. Okay. So in terms of binders, there's a few types of binders that you can select off, which is like boric acid. You can either mix it with boric acid, or you can use it as boric acid to bind it at the side. Then the rest is on the center. The sample is on the center for the measurements. Or some are using, we mix it with some cellulose powder, or some is we mix it with plastic powders. So all those are actually analytical grades powders with very, very low contaminations. Okay. So once everything is mixed, then we put it into the press, then we can press it into pellets. Okay. So in terms of grinding mechanism, okay, actually there are few different way to grind the samples, or to actually to make the samples smaller. Okay, the first thing is by pressure. Then this is normally being done using what we saw in a jaw crusher. When we have a very big chunk of rock, then we put in a jaw crusher. They'll crush it into a smaller size, something like less than 5 millimeters diameters, or less than 10 millimeters diameters. You know? Or then after that, then we go for impact. So impact is normally something like planetary mills or kind of things, or mixer mills, where the samples will bang against the wall of the vessels, and as the process, then the things will get smaller. And the third grinding mechanism is called frictions. This is normally done in the disc mill, where it will, it will rub through the surface of the vessels. Then when it rub through, then they get smaller and smaller, smaller. And then it's shearings and cuttings. So normally shearing and cutting is more meant for softer materials or fibrous materials. Okay. So this is the type of grinding materials where you can use, or you can have in the lab. The very conventional, this is a agate mortar. If you can grind, or you can pound your samples with the agate mortars until the required size, then you can proceed with the XRF. Then the next will be planetary ball mills, where you put your samples into vessels, then you load it with all the different sizes of balls, then the things will spin. Then during the spinning process, the balls will hit the samples, and also the samples will knock on the wall, so the things will get smaller and smaller. Then the third will be a ring mills, where you load your samples in the middle of the ring, and you vibrate the rings, then the samples will be crunched by the ring. And this is the outlook of the jaw crusher, where you load the samples in, so the samples will be, will be hammered by the jaw, so getting in the smaller pieces. Okay. So, but when we talk about grindings, so there's a few points that we need to consider of, which one of the very important thing is the hardness of your grinding materials, and also the hardness of your samples, and also the hardness of the grinding materials or the grinding vessels. So this is example tables of the common grinding vessels or grinding materials. Okay. Normally, in XRF, so beside the hardness, and then they also possible of contamination through abrasions. This is two things that you need to consider of during your, your selections of your grinding process. Okay. In normal days or normal samples or normal applications, we normally suggest customer to use a tungsten carbide. Okay, because the tungsten carbide, the hardness is very high, and it will give you contaminations of tungsten, carbon, and also cobalt. But this is extremely low because the material itself is very hard. Okay. But let's say your element of interest, or you really want to detect tungsten, carbon, or even cobalt inside your samples. So you should avoid using a tungsten carbide vessel. So in that case, which is the vessel that you're going to use? So a lot of people, or a lot of times, then will go for zirconium oxide. Okay. The hardness is also very high. It's about 1002 HV. And this one, it will contaminate your samples with either zirconium oxide or lithium oxide. So if these are not the elements that of interest of your analysis, then you can select these two. Okay. But even that also, the contention levels of these two are actually marginally quite small. For instance, if you are trying to measure today, if you are trying to measure iron ore or some samples, you want to detect the iron. And if you are using a stainless steel vessel, then what we're going to have is you're going to have a much higher Fe on or chromium inside samples. And this kind of errors actually contributes by your sample preparations. Okay, maybe your samples are not really having such a high Fe or high chromium, but because of your, how to say, your vessels is contribute into that. Okay, so this will give you an errors in your measurements. And let's say just now we show you agates. Agates mortar is very commonly used. But if you use your agate to pound some samples, and you can see that in your samples, you're going to have some silicon oxides inside there. Okay. And if your samples hardness are much higher than your vessels or grinding materials hardness, what it's going to do is that you have more grinding materials into your samples. So the leaching process, you leach more condensation inside your samples. So this is something that you need to aware of. Okay. So this is an examples of the grain size effect. Okay. This is the same samples with the different grain size. You can see that on the x-axis is the alumina concentrations, okay, from 10 to 30%. On the y-axis is the relative X-ray intensity. Okay, the same samples with a lesser grain size, the fluctuations or the fluctuation range is very small. It's about 0.45%, okay, or of the mass percentage. Compared to if your grain size is in the much larger size, something is very large as 75 micron and above. Maybe sometimes it's even much larger than 100 microns and above. Then you can see that the same samples, it will not, actually the range, the fluctuation range will be much bigger compared to a much finer grain size. So this is why that we always recommend that you should grind or ground your samples to something less than 50 microns. And once you do that, then you should follow that for your future samples. Okay. Don't grind it at 75 micron today, then 45 micron tomorrow. Then this one will give you errors in measurements. Okay. Then the next process we are talking about will be the press. Okay. Normally in press pellets or in press process, this is the typical kind of press machines that in the market. So we can have a hydraulic press, then we can both are hydraulic. Some is automated, fully programmable, and one is by manual. Okay, then this is the type of die sets or pellet die, where you load your samples inside, then you can press it into, this is the type of press pellet you're going to get. Okay, so the one with the white at the side, this is backed with the boric acid, where normally customers will use boric acid as a backing materials or a packing materials to hold the samples. And some customers are using a steel rings. This is examples of the steel rings. And in some of the industrial customers, they are using a much bigger steel rings. Okay, this is for their heavy duties, because in a day they might process maybe more than 400, 500 samples in a day. Okay, and sometimes we also can use aluminum cups as our backing materials. So it means you put your samples in the aluminum cups, then you load it in the pellet die, then you press it, then it become a pellets. So the good thing about using aluminum cups or steel rings is that this will prolong your life of your pellets. Means your press pellet will not easily break or fall apart, okay, during the the process. Okay, so this is whereas error caused by grinding and pressing. Okay, if let's say the same elements, for instance, which one should we go? Okay, let's say a silicon oxide. Okay, let's say for silicon oxide, okay, if your pulverizing time is getting longer, then you can see that actually your X-ray intensity is getting higher and it will saturate at one time. But in certain elements like SO3, as you grind it for too long, your concentration actually is getting lower and lower. Okay, and also for calcium, it will getting higher. Okay, this is the effect of the pulverizing time. And where else on the other graph, here is the effect of the pressure, the tonnage. If your pressure is too low, then you can see that your X-ray intensity actually is much lower. And you increase the X-ray intensity, let's say for the silica, you achieve as a certain stage. Okay, this is why we say that it's very important to have a consistency. So when you press your samples today at 20 tons, means you need to repeat the 20 ton process in the future. Don't say today I press at 20 ton, then tomorrow I press at 10 ton. So you can see that there's quite a big difference in the intensity. Okay, so this is something is very important. Okay, if let's say we don't want to press, or we have we don't want to press the samples, or we have quite we want to retrieve back the samples after measurements, what we can do. Yes, actually an X-ray, or then we can have another measurements method we call loose powder measurements. Okay, where we have a cup. This is what we call X-ray sample cups. Then on the sample cups, they'll always have sample films. Okay, so we have X-ray films, where normally these kind of films are either mylar, it's a 4 micron, 6 micron mylar, or even sometimes we are using 4 micron polypropylene or proline. Okay, for different applications, then we use different kind of films. For instance, but the best is you try to use the thinnest film, the thinner the possible. Because actually when X-ray, as Kelvin mentioned earlier, when X-ray try to came out from the samples, you need to get through the films. So when they get through the films, actually a lot of this energy is being absorbed by the films. Especially when you try to measure some light elements. Let's say you want to measure, just as what Kelvin mentioned, anything lighter than fluorine, nitrogens, oxygen, or even fluorines. Okay, and if you put the films, because the films are made by plastics, this plastic itself is already contain high amount of carbon, oxygen, and nitrogen. So this will also give you an errors, and your light elements, X-ray, XRF energies will be also be absorbed by the films. So end of day, this will give you a wrong measurements result. For those kind of cases, so normally what we recommended is that you need to press your samples. So when you press your samples, then you put inside the X-ray or your XRF, we can measure direct. There is no protection, or there's no another film barrier which going to absorb your XRF energy. Okay. So that's why this is something that we can go direct. Okay. This is a way that we're going to set up if you have a limited number of samples. Okay. This is Rigaku holders. Okay. And some others. Okay. Let's say we have a very, this is a double pellets. Okay. So we can buy a boric acid. Then inside the boric acid, then we can make a hole. Then we can buy a very small amount of samples. So this one is for very limited number of samples. Okay, this is something that you can get. And this is visualizations of what's happened inside a press pellet die, as we showed you just now, a cylindrical types. So normally we have a die body and a die base, or a male or female die. So inside there, we will put a disc. This is a mirror surface disc. So, and then we pour in your sample, then we start pressurize. Then, so after pressurize, then we can get the pellets out. Okay. So this is examples for some vegetables or vegetation samples. So you can also do the press pellets. Okay. So another very, I'll say, famous way to process your powder samples, especially for geological samples. Okay, for geological samples is by fusions. Okay, fusions is a process where we will melt your samples, or we will digest your samples with a lithium borate flux, where your samples will be digested inside a lithium borate flux in a very high temperature as a 1100 degrees Celsius furnace. So once your samples is being digested inside the flux, then we will pour it out in a casting disc or casting plate, and the samples will cold and will form a bead we call a fusion bead, or it's a glass bead. Okay, it's something like similar to glass. So okay, why fusion process is very important and a lot of people like it. Okay. As we mentioned just now, so powder samples are very subjected to particle size. Okay, so different grain size will give you a different intensity. And also beside that, also powder samples will suffer from the mineralogical effects, and also the surface roughness, okay, preferred orientation, segregation problems. So that's why it's very difficult to do a press powder calibration for ideal XRF analysis, especially when you are looking for a very, very high accuracy of measurements. Okay. For instance, this is examples. The out square, this is the out square of these calibrations by press powder is maybe 0.96. Whereas if we can process it with a fuse bit, then we can always get at least 0.999. Okay, this is the kind of accuracy. If people are looking for that, then this is fusion bits can provide you this kind of accuracy. Okay, so the major problems of X-ray or powder samples. Okay, the first thing, particle size. This is something that we already talked about. And mineralogical is the adsorptions of the coexistent elements. Okay, and also the different phases of the samples. This will cause a mineralogical effects. And also the surface roughness of the samples, segregation problems, preferred orientations. Preferred orientation is something that this is something like the sample is crystallized, so they have preferred orientations. If this is happening inside your XRF, this one will give you some errors in your measurements. Okay, then it's also the statistical control. Okay, so normally this is in press powder. If in process control or industrial, they need to create a very short calibration curve. For instance, this is a silicon oxide. They need to split the calibration curve into a few different range to cover a different range. If not, then you can't really get a very nice linearity on your calibrations. Okay. Well, in the advantages of fusion. Okay. In fusion process, because we are melting the samples into a lithium borate flux. So in melting process, actually we will destroy all the mineralogical effects. So there's no longer a mineralogical effects. And since everything is already being dissolved and melt inside the flux, so there's no longer a particle size problem. And since everything is already digested and melted, so the sample is very homogeneous. And also we can reduce the inter-elements effect because of the samples is become a minority and the majority of the samples of the bit will become a lithium. So there's very low inter-elements effects and it's very easy to handle. And because this bit is a solid piece, so it will not drop into powders or it will not easily contaminate your XRF. And in fusion bit, once you bit or fuse your samples, the bit, if you keep it in the desiccator, this one will last you in a very long time. Maybe in your proper storage, you can last you for maybe 5 years, 10 years without any problem. Okay. And one of the very important why people are using fusion bits are in industry because they can create their own artificial standards. Okay. They can create they calculate the molars of the samples. They can dupe the samples with their required molar of elements, then they create their artificial standards. Okay. So how we can process or how we can produce a bit. Okay. So in the fusion process, we need machines. Either in this picture, this is a fully automated fusion machines. Then beside that, we need two very important ingredients, which will be the lithium borate flux and also platinum crucibles or platinum ware. Okay. So in all the lithium borate fusion, we need platinum ware. Okay. This is very important. Okay. This is an examples of the very nicely fused fusion bits, which is clear, no bubbles and no residues inside the bits. Okay, this is very important because for analysis, if you give him a very rubbish samples, you'll get a rubbish results. Okay. So things is important when you try to do a borate fusions or lithium borate fusions. So the first thing is that your samples must be fully oxidized. You must ensure that your samples is fully oxidized. And secondly, your samples must be representative. Means when you sample your samples out from your sample batch, the samples must be representable for the whole batch of samples. Okay. Your samples must be grounded into less than 200 mesh or less than 75 micron or finer. So that's why I say if you can ground it to 44 or even less than 50 micron, it will be good. even for fusion, it will be very good. Because the smaller the grain size, the easier or the faster the samples can be digest or dilute or digest inside the flux or the lithium borate flux. Okay, and you need to choose a proper flux type because there's many types of different borate or lithium flux with a different concentration of lithium tetaborate and metaborite. Okay, then we need to set our sample to flux weight ratio. This is also important. So once you fluctuate this, the sample to flux rate ratio fluctuate, then your calibrations or measurement result also will give you errors. Okay, and we must ensure that our weighing is very accurate. We have to ensure that the weighing is up to 1 milligrams accuracy. Okay, so and also we transfer the interpreting lab where determining the right fusion program. Okay, because sometimes you need to have a different fusion parameters to ensure that the fusion can be successfully done. Okay, this is the example process. So we ground the samples to as fine as possible and ensure that it's less than 100 mic or even 44 microns. And we weight the samples. In fusion, okay, actually we use a very small amount of samples. So we can use maybe somewhere around 0.3 to about 2.5 gram of samples. But the flux is normally is about 1 to 20 or 1 to 10. 1 part of samples, 10 part of flux. Okay. So once you mix everything together, so the flux can be a lithium tetraborate or it can be a lithium metaborite or it's a mixture of both in the different concentration of both. Then we put it in the platinum crucibles, we heat it in 1000 to 1001 degrees Celsius. Then the fusion time is approximate 20 minutes per cycle. So once it's done, then we can get a nicely formed fusion bead or more like a glass bead. So this bead you can keep in the desiccator, as I mentioned. If you keep it in a very, I would say, low humidity, nicely, this bead will last you forever. Actually it's forever. Okay. So, and this is a typical fusion process, look like a temperature curve. Okay. So normally, okay, the flux will start decompose somewhere around 700 to 800 degree or maybe 900, depends on the flux. So when the lithium flux decompose and start melt, so it will start melt together with your samples. And that we need to, or you will agitate the crucibles, the platinum crucible, we agitate it inside the furnace to ensure that everything is mixed well. So when it's mixed well, we will pour it out into a casting dish or the mold. So when you pour it out, then we go through a very fast cooling process. Okay, this is to ensure that the crystallizations can be happens. So the flux can build the samples and the flux can build a very nice and clean bead. So once it's done, then we passive cool it so that we can take it out from the, I would say, platinum mold in the later stage. Okay. So why we are choosing platinums? Because platinum is very important to have a very high melting points. Okay, and it's very good in mechanical strength at fusion temperature. And it's corrosive resistant, will not react with metal oxide and resist to gases, and salt. Okay, okay, this is something important. Okay, corrosive resistant is with metal oxide. That's why during the fusion process, you must ensure that all your samples are already being converted into oxide form. Okay, so means that you don't put raw metals inside your platinum crucibles, or you don't put your, try to avoid your platinums contact with any raw metals or steel, because any scratches or remaining steel inside your, or metals inside your platinum surface. When you heat it up at 1000 degrees Celsius, this will start to corrode or will oxidize your crucibles, and slowly your crucibles will have a dented and become a hole. Okay, so oxidation resistance, okay, this one will not easily oxidize even at 1000 degrees Celsius. Good formability and weldability, so it can be easily formed, and the good thing is it can fully be recycled. Okay, and this is a different type of flux that available, or this is a common type of flux that which is available in the market. So we have 100% lithium tetraborides to 100% of lithium metaborides, and in between we have different kind of mixture or different concentrations of lithium tetraboride and lithium metaboride. Okay, and there's also one special flux which is called sodium tetraboride. This is not widely being used because this one, the price of it is one thing, and also the availability of this is another thing. So most of the applications in the markets are mainly using lithium's boride flux. And why we have a different type of flux or different mixture of flux is very much depends on our samples. Because if our samples are acidic samples, then we need to have a tetraboride. If we have let's say we want to do a wet chemistry, actually we can use boride to form a wet chemistry digestion process. Let's say we want to digest some things and to feed it into AS or ICP. You can also do it with fusions, but using metaborites. And let's say today we have cement, so we are normally using a 6634, and commonly we suggest a lot of people are using 50-50 because this is a general purpose flux. And actually this is we can cover most of application or almost 100% of application with 50-50. Okay, so if you have a very high silica oxide, then you can have a 1222. Okay, kind of different formulations of flux. And this is a common sample preparation tables. Let's say today you have bauxite samples and you want to fuse it. I can fuse it with 6634. I also can fuse it with many different flux can be used, as you can see in the tables. And either 6634 or 50-50, these two are actually quite common. Most of the samples are okay or can be fusible with these two formulations. And as for the weight, I would say the weight of the samples, normally in this you can see that is 1 part of samples, 10 part of flux. Okay, and in this case we mix in our oxidizer because we want to ensure that all the iron ore is being oxidized, become iron oxide before the fusion process start. And some is without the oxidizer. So this is something that we can use for if you want to go for a fusion process. Okay. So another possible applications for XRF is the liquid samples. The liquid samples can be our normal liquids, oil, cooking oil, or even some wastewater, or even any of your solutions that you synthesize of. Okay. So one thing is by liquid, we can go for direct measurements. Okay. And to measure liquids, we must to ensure that the system are running in helium mode. So that because normally all the XRF or all the WDXRF are in high vacuum modes, in the vacuum modes. So to run liquid measurements, we must ensure that the system are converted into a helium modes. Okay, this can be done by just a simple click on the button on the software. So the system will change to a helium mode. So this is a liquid cell Okay, and this liquid cell is how to say, specially built for tube above system, because normally if you pour the liquids into a cups, the top surface will cover either by air bubbles, or they might have some air bubbles inside the cups. So in this cup design, we can ensure that all the air bubbles are trapped underneath these funnels. So the measurement surface is always clear of bubbles, then to ensure that you can have a very nice measurement result without the effects of the air bubbles. Okay. Wait, what happened? Okay. Okay. So beside that, in liquid measurements, there also another way to run micro, or say very small samples or very little samples, and we can run the measurements in vacuum modes. Okay. In this case, we are using we call filter papers methods, but in Rigaku, there's patented methods of filter papers. In this case, on the right is what we call as a micro carry, where the samples of the filter papers are actually, the outer layer of the filter papers and the inner layers are not interconnects. Actually, it's held by a paraffin wax. Okay, it's held by the paraffin wax. So you pipette your samples in the center of the filter papers, and you dry it, and you put it in the WDXRF and proceed with the measurements. And if, as what Kelvin mentioned just now, we also can do for PPB kind of measurements. Okay, especially for liquids. If you want to go for wastewater and also maybe any fluids, any aqueous samples that you want to go for PPB levels, okay, what we can use is what we call as an ultra carry, where you pipette your samples in the middle plates, or this is adsorption pads, where your samples will be absorbed and dry. Once the sample is dry, then you can load it in the XRF, then you can start your measurements. Okay. By using ultra carry, what we can see, this is the results that we're going to, the ALD that we can achieve from the ultra carry. Okay. For instance, let's say for lead, we can go at 76 ppb, arsenic 16 ppb, or maybe something like let's say, okay, sodium is 76 ppb. Okay, so we can go for from light elements to heavy elements, all in a single measurements. Okay. Okay. So the next also is something we call maybe is the X-ray can be used for polymer and plastic samples. So if you have any polymers or plastics or even rubber samples, you want to know the elemental results, yes, you can go for the measurements. So for polymers, okay, this is let's say today we have resin samples. It's a wire coated resins. Okay. If we go without any treatments, okay, on the y-axis, this is analytical precisions on homogeneity, and the x-axis is the complications, how complicated you're going to process your samples, or you're going to prepare your samples. So the more complicated your sample preparation is, then you can have a much higher precisions or accuracy. If, for instance, if you just cut your samples and you stick it, you arrange it in the flat, then you cover your whole measurement window, then put it in the measurements. Yes, you can do these measurements very easy, but you will not have a very high accuracy. Then the next, if you press your sample in the pellets or hot press it in the pellets, then you also can increase your accuracy. Then if you cryogenic grind it, loose powder, try the measurements, yes, also you can do it. But the best is if you in cryogenic ground in the powders, then you can press it again, hot press it again, then you can have a best accuracy. Okay, this is actually a very good chart, actually not only for polymers, for any of your sample preparations or any of your samples. If you prepare it in a very much better way, then you can always have a much higher accuracy. Okay, this is quite common. Okay, for example, if you today you have a very small or very limited samples, what are you going to do? Especially in a lot of cases when you only can synthesize a bit of your samples and you try to recover back the samples after the measurements. Can we do that in XRF? Okay. Normally, if you do the small tiny amount of samples in ICPs or AA, you will not be able to retrieve back the samples. But in XRF, there's also a way that we can do small samples or limited samples, but end of the measurements, if you want, you can still retrieve back your samples. Okay. There's two things. Okay, this is actually beside what Kelvin, or beside the advantages of having micro mappings. Okay. There's also some accessories from Rigaku that you can allow you to run with a tiny bit of samples. Okay. For instance, in this case, we have a special sample carrier where you can just put a tiny bit of samples to cover the center of the hole. Then you put it in the X-ray cups and you put it in the measurements. Okay, this is one thing. If you have a very small piece of samples, very small, maybe let's say 1 mm or maybe 2 mm or maybe 0.5 mm kind of samples, either it's a solid piece or maybe it's a tiny bit of samples or powders, you can stick them on the top of this screw. This actually is an acrylic screw that you can stick your samples on top. Then you put in the cups, then you go for the measurements. This is a kind of additional accessories that you can achieve with this kind of sample preparations. Okay. So I think, okay, that's all for my sharing today, and hopes everyone enjoy and understand, learn something from this sharing. Okay, thank you very much. So
Okay,
I'll
thank you,
pass
Mr. Loy.
the
So we have a question
yeah.
already. Is
Yep.
the software able to correct preferred orientation?
No. Okay. So actually the WDXRF, if let's say your samples are having a preferred orientation, what we can do is normally we will spin the samples. So this is why one of the reason why we do say spinning, but even that also will not help much in the preferred orientation. But normally preferred orientation will be for XRD.
Okay, any other question from the floor?
Hi, Mr. Loy. Sorry if I can ask directly. I'm Tuti from USM.
Okay.
Is there possibility that the sample will volatilize or the some of the elements might lost during the fusion method?
Yes, you are right. So some of the volatile elements like mercuries or the volatile materials will vaporize during the fusion process.
Okay, so how about the results? It might disturb the result, the accuracy of the
So
result.
yes, so end of the day, the results will actually show you a much lower concentrations of those particular volatile elements.
Oh, okay. So, thank you.
That's why if you have volatile elements that you plan to do the measurements, it's always good that if you can do it in a press pellet form.
Okay.
Oh,
So
there's a
it's,
question.
so we must know very well the samples, right?
Yes.
Okay, Mr. Lloyd, after this application sharing, right?
Okay, so after this, Kelvin will take over again for the applications.
Okay.
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 So I think next will be, we can pass it to Kelvin if there's no any other questions.
There's one question from Azarin.
So Azharin, to what depth of the sample metal the accuracy of this method acceptable?
What type of samples? Okay. So that's why it's also very much depends on your metal samples, type of metal samples. Let's say for aluminiums. For aluminiums, the X-ray penetration depth will be much deeper compared to, let's say, irons or even, let's say, a gold. Okay. So that's why in many, I think recent years, we have many cases of Ahranu, pajak gadai, then being cheated by syndicates where people are pajak gadai their fake gold, or it's a gold but it's a coated gold. Okay, because Ahranu nowadays are using X-ray. Mainly, a lot of Ahranu are using XRF as their, I'll say, measurements or control tools. So for gold, for instance, XRF penetration on gold is just maybe it's less than 10 microns. So anything beyond 10 microns underneath the top coatings of gold, XRF, we will not be able to detect that. Okay. The primary X-ray from the X-ray source, we can go very deep. We can, I'll say we can penetrate the whole metals without any problem because the primary X-ray is at 60 kV or maybe 50 kV and very high power. But the issue is that the excited XRF from the sample itself, let's say for instance, we want to detect, because normally, let's say the fake gold inside is, they cover with the tungsten. We want to measure the tungsten coming out from the gold. So the tungsten XRF will have difficulty to pass through the gold layer as this XRF energy will be absorbed by the gold before they even manage to release out from the gold surface. Okay. So that's why a lot of cases we say XRF are more like a surface analysis because we don't really, and we have to assume there's always assumptions that we need to assume that the samples is always homogeneous for any of these measurements. Okay.
Okay. Next question. Can SRF measure the semi-solid sample? The sample turn into liquid once exposed to the heat.
Okay, yes, sure, it can. So let's say you have something like a paraffin wax, or it's a wax, or maybe it's something which is much lower liquidization temperature. If your liquidization temperature is very, very low, then you might need to do it as a liquid measurements samples. So you can prepare your samples in the liquid cups. You can do the measurements. If let's say your samples is in paraffin wax, I think you can do as a normal measurements, or you can, as a protection, you can do it as a liquid measurements methods. It's also possible. Or let's say you want to measure some gel, it's also okay, no problems. The method is actually similar to the liquid measurements methods. And the very important is that you must run your samples in the helium modes, not the vacuum modes.
Okay. Is any
Can I ask a
any
question
question?
through voice? Yeah, I
Okay.
would like to ask about your what do you call that uh the compacting factors is actually affecting the accuracy of the measurement. So how do you correlate it with the standardless method to quantify your elements? Because if everything is always changed, then there's no way for you to actually compare to a standardless method.
Okay, very good question. Okay, actually, in standardless, when you compact the samples in a different compactions, your intensity of because when during standardless measurements, we are not only looking at the one particular X-ray intensity, we are looking at the overall X-ray intensity. Means that's why in all the standardless measurements, the system will scan for all the available elements inside the sample. So the first thing is the software will identify all the available elements inside the samples. From there, then they will do the calculations based on the relative intensity and also together with the what we call scattering intensity. So based on the scattering intensity, then the system will know that actually how much or how compact your sample is. Or this is something that there are a lot of mathematical formulations actually is being considered inside the standardless measurement methods. It's not very direct. Not to say that we want to measure for silica inside the sand. The software will just look at the silica intensity. So besides looking at the silica intensity, the software or the system actually will search for all the others coexistent elements inside that samples. Then from there, they'll recalculate. Then based on the intensity of each element, then they give you the quantified, semi-quantified value.
Okay, we have another question from Dr. Josephine. If the quantity of the powder sample is very little, is there any solution to do the measurement?
Okay, if the quantity of the powder sample is very little, yes, that's why I think the last slide is about the very tiny little bit of samples, where that's why it depends how little the sample is, then we can, because the tip of the screw is about, I think the tip of the screw is about 2 mm diameters. So if the samples can be put on the tip of the screw, then we can perform the measurements. Then with the samples, tiny sample holders and the micro mapping functions, then we can quantify that small quantity of powders.
Okay. Any other question? No. Okay. So before I pass the last session back to Mr. Kelvin, after this, Mr. Sazwan will share feedback form in the chat box. So I would like to remind you all to complete the feedback form. Okay. And then if you complete the feedback form, then we can give you the slide for this seminar and the recording. Okay. So I pass the last session to Mr. Kelvin. Thank you.
Okay, thanks, Mr. Aziri. Okay, so now everybody can see my screen. Okay. So the last section is mostly about the application part, whereas most of this application also can be done in the UKM i-CRIM machine over there. So basically, there is like kind of like a 10 section for this what do you call that, the feature which is available in the Primus 4 in the UKM system. So we're gonna go through it one by one. So just to kind of like give you an overview about what is actually the instrument capable of doing. And also in the last part, we're gonna talk about any future expansion if there is a need. So firstly, it's actually what we always mention, this Primus 4. 4 is actually a tube above system. So in comparing with the mostly the tube below system, the tendency of the sample drop on the actual tube or the detector itself is actually very minimized. So even we are doing the liquid sample and also loose powder sample, there is no this kind of problem. Nevertheless, for the loose powder and the liquid system, we will need to do inside the helium. So which it could be also limited what is actually the element that can be measured, especially in the light element. But if you actually, your sample itself, let's say it is actually you are measuring a bulk sample, and then with the crystal that is actually available, then you can go to as low as like the starting measurement from the oxygen. So this is actually the crystal itself is actually one of the most most important part that determine the capability of the WDXRF system. So what is available in the UKM is LIFT 200, PTH, GH, and RX26. So as you can see in here, right? So RX26 can allow you to measure starting from oxygen, whereby the LIFT 200 allow you to measure on the cesium. So which means this one is actually can cover the light element as well as the heavy element and the rare earth element. So in the future, if there is a need to be like focusing on the rare earth element, LIFT 220 crystal can be added. Or if actually there is a need to measure even lighter element, for example, just now people are asking about carbon, RX61 and RX61F can be actually added into the system. The good thing is actually now it is only using 6 position of the 10 crystal position. So another additional 6 crystal can be added into the system to expand the capability. So normally in WDXRF, the lifespan of the WDXRF can be 20 years. One of our 20 to 30, even 30 years. One of our older system is actually, it was in the USM until actually the system cannot be even upgrade or further repair anymore. So that time I remember it was about 20 years. So throughout the lifespan, it actually can be put a lot of things. So one thing is actually for the older Rikaku system, right? The default is actually having a curved crystal. By having a curved crystal itself, right, you actually improve what you call that the intensity, because actually the X-ray is going to be more focusing. So in the work, actually this can actually improve the low limit of detection LD. So this one is actually kind of like the summarize of what Mr. Loy have been mentioned just now. So currently the system is capable of measuring like the fusion bead sample, pressed powder sample, loose powder, small amount of powder, or even small piece of solid. You mentioned solid in here. Nevertheless, like what Dr. Josephine asking just now, if your sample quantity is very small, you also can put on the tip of the ear. And general liquid sample. This one is actually liquid sample that we can use in measure in the helium environment. If your sample you want to go for trace amount or like a ppb or sub ppm sample, liquid sample we actually can use this so-called ultra carry. And solid sample in here, the holder, if I remember correctly, can put up to 51.5 millimeter of sample. as long as your sample can be fit into that holder, it can be measured. Of course, the surface has to be flat, so you can either polishing it or something like that. So which gave it a very wide capability of what the system can do and measure. So of course there is actually vacuum and also helium available. So even loose powder or liquid sample can be measured. The good thing about this ultra carry, it allowed sample to measure in the vacuum, which actually improve the LLD. So later on, I'm going to talk a little bit more about this ultra carry application. So another thing is actually this auto pressure control, which is we call it APC. So this one, as you just now in the first section we mentioned, air, helium, everything, it actually will absorb X-ray, which in terms of actually it affecting the accuracy of the light element. So by having this APC vacuum setting inside, once you enable, right, it will actually keep the vacuum in a very, very good constant of 13 Pascal. So in this table itself, you can actually see fluorine and oxygen itself, right? The vacuum degree is actually affecting the relative intensity in the measurement. So if you want to do a very light element, right, by having this one at a constant value itself, right, you eliminate the error coming from the instrument, which improve the measurement accuracy. So this one is actually normally it is disabled. So because if let's say you are measure a relatively heavy element like sodium or and above, this is not important. But if you actually going in for the light element, please let UKM people know about it. They can enable this function. So another one is actually about the tube BE window, the tube window. In the first section, we are talking about three major things, which is actually relatively to the tube. One is voltage, second is actually current, third one is the window itself. The window, which is a BE window, beryllium window, this part, this is actually where keeping the air from going in and allow the X-ray to coming out from the tube itself. So this is actually where the X-ray coming out from. So as you can see in here, right, different type of thickness of the window is actually affecting the intensity of the X-ray. So which means by having a B30 micron tube, the X-ray relatively intensity of the tube of the system is actually affecting very largely for the light element in here. So which means it, or compared to the conventional 75 micron tube itself, the intensity that you can see from the measurement itself is going to be higher. So some of the systems actually can improve increase the tube current. So you can see by adjusting from 150 milliamp to 170 milliamp, you only improve 20% or 2% of the intensity. But if you actually decrease the tube window from 75 micron to 30 micron, you actually improve 40% of the intensity. So having a tube which is 150 milliamp is much economical compared to having a tube which is 170 milliamp, whereby you actually improve the intensity a lot. So that's why this is actually an overview of primers for lower limit of detection LLD. So this is actually for the oxide powder, like in the measurement in the vacuum, this is the diameter, counting time, and so on. So you can see even for the very, very light element, we actually from fluorine, we can go for 19 ppm. So this is actually compared to this powder sample. If we are talking about ultra carry measurement method, this result can be further improved to ppb level. But this is actually, of course, this is just a general guideline of this measurement LD. Whereby actually, if we talk about different, let's say just now you remember we measure light element in a copper or very heavy metal, the LLD itself is actually going to be increased more than this number. So it is very important to know okay, you don't need to know exactly what is actually the element content before you do the WDXRF, but it is important to know what you are trying to measure, what kind of result you are anticipate. So let's say if you are talking about, I would like to measure, for example, calcium, and then I would like to see the ppb level. By all means, this might not be a good technique for you to use, and you want to actually go for ICP. But if you actually want to say anything, measure anything above this kind of general guideline, then you can go for XRF. And also, okay. So the next one is actually just like kind of like give you an like reminding about this semi-quantitative analysis. So semi-quantitative analysis itself, right, it is so-called a standardless analysis method, as what we mentioned, talk about in the first section. So the instrument itself, right, it uses a pre-measure internal library, which contain a lot of different type of element measurement intensity inside there. From there, they calculate what is actually the theoretical intensity and compare with your measurement intensity. If both of them meeting each other, then they will converge and return you with the result. Okay, so this is actually what happened inside there. That's why for this standardless analysis, right? The instrument will measure all the elements. It will default measure all the elements starting from foreign all the way to CCMS 96 cm. So unless you tell the instrument that my sample definitely doesn't contain foreign or definitely doesn't contain certain element, so you can remove that measurement to save you the time. But in the default, it will actually measure everything so that actually can do the quantification. So in the measurement, it will return you the intensity of the element which it detects. So you can see from this on the left hand side, for example, this is a silica peak. So you can see this is a very prominent peak inside here. And then you can see, look at here, for potassium itself, there is no peak itself. That's why you cannot see any intensity in here. So this information can be shown to you if you're doing the standardless analysis. So normally when we actually giving the customer, we might give them this result and also this curve itself. If actually this is actually for us to prove that actually this particular element is existing in your sample. So by comparing this intensity with the internal calculation theoretical intensity, if it converge, it actually give you this semi-quantitative end result. So the semi-quantitative result, the accuracy could be about 95% or even sometimes lower to be like 85 or 80%. So because this is actually not a calibration method, but the advantage of this SQS, standardless measurement, is you don't really need to have the standard. But you also one thing, remember this one is actually before that, there's an assumption. Assumption is that before we use the FP method, element which distribute homogeneous in the sample, this can be easily be done as long as you grind the sample to 75 mesh and below. You can create a very good homogeneous. But there is a few things which we actually very difficult for us to do. Okay, for example, some of the light element that is not possible to measure in the XRF if you don't have that particular crystal. Sorry, I jump a little bit the sequence in here. So, and also that if you actually have say for example, you have some sample which you send for ICP, and you already know the result. Then if you want to improve the standardless, is you actually can put in this particular one or two standard as a matching library. So compared to this, with using the default library itself, right? It will just check the default library, calculated the theoretical intensity with the measurement intensity. If converge, give you the result. This matching library itself, right? It actually allow you to put in so-called a standard. Of course, this standard is not enough to form a calibration curve. So when we talk about a calibration curve, the minimum standard we need is actually at least 3 and above. So to give you a logical calibration curve. But a lot of times, right, especially in the university and also research institute, don't have the luxury to have a lot of different standard because everybody also doing different things. It doesn't make sense. So if you already have one or two non-sample, then you can make it as a standard and put it as a matching library. So this is a function of this what you call that Primus 4 and actually the software that allow you to add in the internal standard. So this one, it will actually calculate the standardless by referring to this so-called the matching library standard that you put in. And also there is very easy to add. So if once you can have a standard, they say please add in as an internal standard. This is actually my value. They can actually just add in the system itself. And in the UKM system, right, they also have so-called a master matching library for raw sample. So what you Rikaku do, right, is actually using a set of actually non-raw sample standard and add into what you call that, the matching library function. So this is actually the available standard that is available inside there. Then this is actually the content of the different value itself. So if you actually have a sample that is relatively close to all this sample, you actually can automatically pick up to form a matching library. So you can see this is actually like a example that which they measure. This is a certified value. The silica is a 50.96. If you're using the common library itself, right, it actually come out to be 48.3, whereby if you're using the matching library itself, it actually improved to 49, subsequently of all the other elements itself. So this matching library is for the raw sample. This is actually already built into the system. So another thing which is actually, this is another function so-called scattering FP method. So just now when we talk about some of the pre-requirement of it is not showing in here, sorry. But anyway, so what we are talking about the FP, when we're talking about FP method, right, is the FP method, in order for it to be mathematically correct and give you the result which makes sense, supposingly all the elements that inside your sample need to be measured and need to be able to quantify. But we know that actually there are some light elements like hydrogen, carbon, nitrogen, oxygen, and carbon that we are actually not measuring. This problem happens especially when your sample contain a lot of organic component or even plastic. The result could be totally wrong. So how does Ricardo tackle this problem? Is by having all this so-called scattering FP method. So this scattering FP method itself, right, it will actually estimate the unmeasurable element by using the Compton scattering. just now in the first part of the presentation, we talk about there are two different phenomena, which when the X-ray hit the sample, one of it is actually a Compton scattering. So a Compton scattering in the previously people thought about it as a noise, but in fact, right, it actually giving us some information to allow us to estimate the non-measurable item. So that's why this is a function that can be enabled. So in the software itself, right, there is actually this part which is called estimate non-measurement component. Once this select, it actually allow it to be measuring this function. So you can see that this is actually the peak for the Compton scattering. So you can see the rock itself, it is relatively small. And then limestone is like this, because limestone also contain a lot of carbohydrate material. And then it actually mostly in the plastic material. So in the previously, right, you actually can say for the software to estimate carbon, oxygen, this like individual one of it. But if for a sample itself, it can be contain a lot more than carbon, oxygen. So this scattering FP method itself, right, it actually allowed you to estimate all these things by using the Compton scattering this part. So again, in here, they show you what is actually the result. So if you're using the scatter method for sodium, the standard value is 0.9, and then estimated value is 0.69, and the magnesium is 1.28, and this is compared to 1.22. In compare, if you only estimate carbon or oxygen or so on, the result is actually much better. But of course, if you already using another type of method, like for example, CH analyzer or something like that, to measure precisely what is carbon content, what is the hydrogen content, and so on, you also can put in this value into the system that actually improve you to doing the standardless analysis. So this is another example for this thing, especially on this polypropylene sample. So you can see that actually how it actually improved the result by using the same scattering FP method. Okay, so just now we guess I think quite a lot of people are asking about this. What is the possibility to measure for a small area of sample? So the answer for all those questions is actually micro mapping, or even though it is called mapping, but you don't really need to do a mapping if your sample is very small. So the smallest spot which is available in the Primus 4, it is 0.5 mm and 1 millimeter diameter. So if your sample itself is actually bigger than this size, or equivalent, or slightly equivalent, you also can do this kind of measurement. So if you actually your sample is actually a little bit curved itself, right? Because of the part that we are measuring is very, very small. So the cavity, it might not affecting so much. And one thing is actually, just now we also mentioned about the X-ray intensity. It is not actually the highest intensity is not at the middle part. It's actually shifted to the left hand side. So when you actually doing this type of measurement, the hardware of a Primus 4 itself, it will automatically measure at the part where the highest intensity is actually having the highest intensity. Then you actually can increase the measurement intensity of the sample. Okay, so one thing is like another thing is important is to bear in mind, if your sample is very small, then you're using a very small spot to measure the point. In order to get a very good result, you will need to longer the measurement time. So for example, if you're measuring in the 30 millimeter, it takes about, let's say 10 minutes to complete the measurement, to complete the full scanning of all the elements. In this micro mapping, you might need to increase it to maybe 30 minutes or 40 minutes, depend on how many elements you want to measure. So just now we mentioned this is actually a mapping function, which means we actually allow you to map the sample. So this is an example. This is actually the holder that put this rock on top of sample. Then that is a camera for you to take the image of the sample. So once the image has been taken itself, right, you can actually choose even the particular point you want to measure, or you actually can select the area where you want to measure. So that will go through it. Like let's say, for example, I put 10 points at this one and 10 points across here. So they will measure total of 100 points in here. So it will actually give you a very clear mapping about the element distribution inside the things. So you might be asking, so we can also grind the sample into a powder, then we can get a homogenized result. Yes, that is correct. You can grind the sample, make it a powder, it gives you a homogenized result. But there are certain applications whereby, for example, just now we talked about the bone. So if you want to see how the element distribute inside the bone, you might need to actually, you won't be able to grind it, because once you grind it, you lost the information about the particular information. Like for example, let's say if a bone is polluted by a heavy element, it might actually have some deposit inside the bone, whereby this kind of micro mapping can help you to do the job. And of course, then after that, we can actually display the result at the different things. For example, this one, they show that magnesium at this area, it contains the highest magnesium at this black color part. At this aluminium is actually, aluminium is actually mainly distributed at this part of the sample. So we know this actually this white color part is actually aluminium, and whereby this iron is also content in here. So this kind of information, right, it is also very important if you want to do the micro mapping for XRD. So because XRD also have micro mapping, which is available. If you guys need that kind of measurement, yeah, let us know, because we do have some few customer who is available to do that kind of things, that kind of analysis for micro mapping XRD. And this is another example of using this sample. And this is actually the result. The result can be displayed in this color code, where you can see this display of distribution of the element in the sample. It also can be actually showing you according to this kind of like a table. So this is one example, another example, which is they're showing they compare two type of rock. One is shell, one is slag. So this sample itself is actually a very small sample. So they want to see what is actually the content on here, because this is very important when people want to do the drilling application, that they want to determine what kind of drilling fluid which they want to use. Namely, it's actually water-based or oil-based. What if they actually the rock, most of the rock is actually contain those clay mineral, which is actually hygroscopic. It means that actually it can absorb water and then doing stuff shelling. So for those kind of actually sample, those kind of rock, right, they cannot use the water-based drilling map. They will need to use in the oil-based drilling map. So by measuring using the micros analysis itself, right, they actually can help them to determine what is actually the clay mineral which is present in the sedimentation rock. Then namely to give you this kind of the information. Then from here, geologists will be able to tell, okay, if I contain this kind of element, they can actually be what type of clay, and then determine what is actually used to tackle this kind of drilling condition. Of course, if they want to be more precise, they can also go for micro XRD. So but your geologists, roughly they see this one, they will know that what kind of clay they can contain inside the sample. So this is actually a summary of part of the application that can be used for micro mapping. So for example, it can actually using to identify a very small part. So if you only measure, if your sample is very little, then you don't need to do the mapping. You just do a spot analysis, whereby where you want to do the whole mapping can also be done. Another very important is actually the contamination in your sample process. If let's say, for example, this example is available on the Rukaku website. So this is actually by right, this is the formation of this sample. It should be at this color, but after the process, they actually have all these black spot. So what micro XRF can be done is actually they can identify what is actually inside here, so that they will know what's wrong with the process. Another one is very important for geologists when you actually going to do the core drilling. So if you actually want to know about what is actually the mineralization process, could be there is actually volcano eruption that coated the whole layer on with one particular type of mineral. Then you actually can do a cross section of the drilling core, and from there identify what is the sedimentation throughout the time. So this micro XRF can give you a timeline in terms of if you correlate with the timeline, how many millimeter it can be, 1 year can be sediment and cover. Then you can actually give you a timeline of the Earth progress how to say event. So that was a micro diffraction. So the next one is actually PPB analysis with this microcarry, as what Mr. Lloyd had mentioned just now. So what we mentioned is actually what you call that? XRF itself is actually a very good instrument to cover from ppm all the way to percentage. If we actually want to measure, let's say, PPB in the liquid, firstly, this ultra carry only can be worked on the liquid sample, and it doesn't work on the oil base, because one thing very important is the sample has to be able to dry. So what is the advantage in compare with the general liquid method in here is this measurement method can be measured in the vacuum, which makes it a very important part for the measurement. So why this one is actually why this filter paper can improve the LLD is actually when we look at the calibration curve. If you want to improve the LLD, there is actually a few methods to do it. One is actually you can increase the slope of calibration, which means your calibration is intensity go higher, and then the percentage kind of reduce. So which means you're shifting the chart to this location. Another one is actually you decrease the background. So increase the calibration curve is actually kind of like you can achieve it by increase how many sample you can measure at one time. What is the volume or what is the gram or something like that. Decrease the background is actually you in terms of what you can do is depend on what is the medium you are using it. So in the conventional filter paper, right? Firstly, it is very thick. This sample paper is very thick, which actually contribute to the background. In compare with this micro carry or ultra carry itself, it is very thin. Another one very important thing is actually, it actually can allow you, even though it's thinner, but it allows you to absorb more sample, like 500 milliliter, compared to this conventional filtered paper. It only allows you to dissolve 50 to 100 milliliter at one time. So in here, this is why we actually achieve two important aspects to improve the LLD, one is actually we can measure more volume. Secondly, is actually we reduce the background. So the sample preparation part of it is actually you can drop the liquid sample on here and allow it to dry. Of course, that you can let it dry outside at the air, or you can actually using a vacuum drying cabinet to let it dry faster. So this is actually the two methods to do it. So what we can see inside here, as you can see, with this ultra carry itself, right, the background itself is significantly reduced, and the intensity itself is significantly higher. The PB ratio is going to increase. Compared with this filter paper, you have a very huge background, and the intensity is actually much lower compared to this thing. So what we can do is actually this is a kind of like a rough detection limit. So all these arsenic, PB, chromium, fluorine, all these things, this is actually in PBB, and then this is PPB, and this is a ppm level. So this is also PPB level. So this method itself, right, it is good in terms of if you want to have another method, if you want to compare your measurement result with this what you call that and your ICD result. And also secondly is if you want to measure the sample, which elemental content could be from very low all the way to very high, this one method itself actually can be using. So this in here we show in two examples. One is a river analysis. So this method itself, it actually require a calibration. So you can actually using your ICP as to give you the secondary standard and calibrate the machine. So you can see that in the PB, this is a 10 ppb peak. So one thing, as long as actually you can see the peak in the XRF, you can quantify it. And the good, if you want a good measurement, meaning that you need to get a good peak. So you can see this very low concentration itself, you actually also can give you a very sharp peak. So that one is actually meaning actually you have a standard. Another one is actually we also can be using this what you call that standardless analysis to quantify this using on the ultra carry. So this is actually the SQS result, whereby this is compared with the standard value. So when you actually run the ultra carry standardless, it is the same as what you run in the powder, except the program, there is a program for you to choose already. So just now we talked about a lot is about the standardless analysis. So now we are actually going to be more focused on what is the standard which is available in the UKM. So mainly they actually contain this limestone, which is contain a lot of other different rock sample, and there are cement standard which is also available, and also mineral raw material which is also available. So this is actually this is actually the available geological standard that is actually available in the UKM. So one thing important is actually this is actually the concentration which they are available. So for calibration, we actually not saying must be within the standard, but it is good to be within the standard, which means the measurement is accurate if your measurement result is within 28.2 to 74.9. And this standard itself is available in the fusion bit. So meaning actually fusion bit in the second presentation we did talk about it eliminate a lot of mineralogical effect, particle size effect, and so on, which make it a very homogeneous sample. So your sample, if as long as it's within this kind of range itself, it can be measured. And also that this is a geological standard, And also that what they have is actually cement standard. So cement analysis is actually available in these few different processes itself, like from quarry to raw material, all the way to the end product. So if anybody from the civil engineering side, they are doing the research on the cement or the raw material, UKM machine also can help you to do the machinery. Then this is actually the major element which is that you cement industry is interested. Calcium, silica, aluminum, iron, and also some minor element, and also some trace element. So trace element which unfortunately is not very much available in the what you call that in the UKM machine. But if you are doing the trace element, most likely what happened is people using alternative material. So nowadays, right, we see a lot of cement industry, they are starting using the alternative material, which means they're actually using the like power plant fly ash as one of the subsidy for the day-to-day raw material, or they are using those like garbage which after they send for power plant burning, they're actually also using it as one of the raw material. So those raw material itself, they will need to check for the heavy element content. So UKM machine will be also able to do it, the analysis. So this is actually the NIST standard available. Mostly it's actually all the cement standard, so which can cover this kind of range. And this is some example calibration curve. So this is actually a fusion bit curve. As you can see, that actually is very, very linear, and the correlation is actually very good, about 9 point something. This is a few example. Silica oxide, sodium, even sodium is actually a very low concentration, very, how to say, very low concentration is very low, and the intensity is very low. They also can get a very good correlation. And this is actually the available mineral raw material. Mainly is actually this raw, and this is actually the concentration which they cover. So which means actually if your sample, it is available, is actually roughly around this kind of range, it can be done. So good thing about UKM i-CRIM is actually they also have a fusion machine. So even you give them the raw material in the powder form, they can also make it into the fuse bit. Subsequently, they can use this calibration curve to do the measurement of your sample. So this is some future analysis expansion. So of course, one thing is actually they still have a lot of slot that they can add in different type of crystal, so to expand the measurement capability. Another one is actually, I think it is becoming a very attractive for in terms of the trace element pack. So just now, people have people asking about some of like volatile element or kind of trace element or something like that. So unfortunately, volatile element and also trace element itself, right? Trace content itself, right? It might not be very good to do in the fusion bit. So there are two reasons. So firstly, volatile element will be get vaporized when you're doing the fusion process. And if you actually go for the trace element, because remember when we do the fusion, we will need to dilute it. So mainly it's actually 1 gram of sample, you dilute, you put in 10 gram of flux. So the dilution factor is already 10. So if your sample is actually ppm, then you dilute it, it will be further reduced. So for those kind of sample itself, right? Normally we will do press pellet so that we can actually measure the trace element. So in the trace pack itself, right? This is actually the element that is content. So we actually see quite a lot of customers, they are very interested in this rare earth element, LACE and the other things. So this package itself, right, it actually cover this type of element, and also the major element can also be measured inside the sample. and then it automatically correct all these matrix correction in this trace pack. And this is actually the analysis range for the trace element. So you can see that actually mainly is very low concentration. So because all these type of element is actually naturally it actually the amount is very small. Okay. And this is actually the measurement condition. So this package itself, right, it will automatically already have all these things. And this is actually the LLD. What is the lowest value it can measure? Okay, so yeah, this is my overview of the application which is available in the LUCAM. Okay, Mr. Adli.
Yes.
Yeah, so I think yeah. So that's the end of my presentation.
Okay. Oh, we have a question from Shima. What is the minimum thickness of sample for mapping testing?
I will say it is not really the minimum thickness of the sample. Is actually really depend on what is the type of sample that you are measuring. So for example, let's say so with the thickness below 1 micron, and if it is a polymer sample, let's say if a very light element, it actually might penetrate through it. It will just shoot through it. But if you actually have let's say for example, a metal sample, it will just able to do the measurement. So what kind of sample is this 1 micron thickness? This 1 micron is very thin.
Yep, I think some add up from my side. Okay. So for 1 micron, I think the most difficult part is how to hold the sample. Okay. If let's say you're going to support the sample on top of a film, as we mentioned just now, is the the thickness of the samples, because the X-ray going to penetrate a few microns. So we're going to get some information also back from the back support. So let's say you put it on some substrates or some films, the films also will contribute to the readings. So this is something that what you're going to get from 1 micron of samples.
Okay.
So
Any other questions?
in short, like probably you can for sure you can get a quantitative result, but you can get a qualitative result to understand what is the element inside there. Maybe the quantitative result is it might be affecting by the supporting things behind.
Okay. Any question from the others? No? Okay. So I think we have come to the end of our webinar today. So I would like to thank Mr. Kelvin and Mr. Loy for their time and then for their effort and then for their knowledge. Okay. And then everyone for joining us today. And then, but before we end our webinar, I would like to ask all of you to turn on your camera for photo session. Can we have the copy of this recorded seminar? Norliza, after you fill up the feedback form, yes, we can give it to you. Okay, Sazwan ready ke?
Boleh. Okay, tunggu semua dulu Okay, ready? Smile. 1, 2, 3. Okay, thank you.
Okay, thank you.
Thank you.
See you again.
Thank you.
Okay, bye.